According to the National Electrical Code, specifically Article 250.30 at WO, a neutral conductor must be provided for all electrical systems that have any phase conductors connected to the system. This requirement means that even if all the loads in an auxiliary building are three-phase, a neutral conductor is still necessary. The presence of a neutral conductor is crucial for several reasons. Firstly, it provides a return path for unbalanced loads. Three-phase loads are not always perfectly balanced. This imbalance means that one phase may draw more current than the other two phases. The neutral conductor provides a dedicated return path for this unbalanced current, effectively preventing it from flowing through the equipment grounding conductor. Without a neutral conductor, the unbalanced current would seek alternative paths, potentially causing unwanted currents in the grounding system, which can lead to electromagnetic interference, and in extreme cases, pose a safety hazard. Secondly, the neutral conductor serves as a reference point for grounding. In an electrical system, the neutral conductor is used as the reference point for grounding the system. Grounding ensures that all equipment within the electrical system is at the same electrical potential. This equipotentiality is vital for preventing electrical shocks. If different pieces of equipment have different electrical potentials, a person touching two pieces of equipment simultaneously could experience a dangerous or even lethal electrical shock. The neutral conductor connected to ground at the service entrance helps maintain this equipotentiality. Thirdly, the neutral conductor provides a path for fault currents. In the event of a fault within the electrical system, such as a short circuit, the neutral conductor provides a low impedance path for the fault current to flow back to the source. This low impedance path is essential for quickly tripping over current protection devices, such as circuit breakers or fuses. When a fault current flows, it causes a rapid increase in current. The overcurrent protection device detects this increase and interrupts the circuit, preventing damage to equipment and protecting personnel from electrical shocks. Without a dedicated neutral conductor, the fault current might have to travel through less predictable and higher impedance paths, slowing down the response time of the overcurrent protection devices and increasing the risk of damage or injury. In a 277/480 volt system, the neutral is derived from the center tap of the Y-connected transformer. This center tap is grounded, establishing the reference point for the system. The 277 volts is the voltage between any phase and the neutral, while 480 volts is the voltage between any two phases. The neutral is essential for providing a stable voltage reference and facilitating the proper operation of 277 volts loads, if present. Consider a scenario where a three-phase panel board is fed from a 480 volt source, but there are also 277 volts lighting circuits. These 277 volt circuits require a neutral connection to function correctly. Even if the primary load in the auxiliary building is three-phase 480 volts equipment, the potential for future addition of 277 volts loads or the presence of control circuits that require a neutral makes it prudent to install the neutral conductor. Furthermore, the NEC mandates the presence of a neutral conductor under Article 250.30 at WO, regardless of the current load configuration. This requirement ensures a safe and reliable electrical system, accounting for potential future modifications and unexpected conditions. Ignoring this requirement can lead to code violations, safety hazards, and potential equipment damage. To further illustrate the importance of the neutral conductor, consider a scenario where a 480 volts three-phase motor is connected to the system. While the motor itself does not directly use the neutral conductor under balanced conditions, any control circuits associated with the motor, such as those used for starting, stopping, or monitoring, may require a 120 volts or 277 volts supply. These lower voltage circuits are derived from the phase to neutral voltage, thus necessitating the presence of a neutral conductor. Furthermore, even a perfectly balanced three-phase motor can experience temporary imbalances due to variations in the supply voltage or internal motor conditions. These imbalances can create neutral currents, which need a return path to prevent voltage distortions and potential damage to the motor. The NEC requirement for a neutral conductor is not simply a matter of convenience, it is a fundamental safety measure. It addresses potential issues related to unbalanced loads, grounding, and fault currents. By providing a dedicated return path for neutral currents, the system ensures stable voltage, minimizes the risk of electrical shocks, and facilitates the rapid clearing of faults. When designing and installing electrical systems, it is essential to adhere to the NEC guidelines and prioritize safety. The inclusion of a neutral conductor in a 480 volts three-phase system, even when all the loads are nominally three-phase, is a critical aspect of ensuring a safe, reliable, and code-compliant electrical installation. To summarize, the reasons for carrying the neutral to the auxiliary building are threefold. Firstly, it provides a return path for unbalanced loads, ensuring that current imbalances do not flow through the grounding system. Secondly, it serves as a reference point for grounding, maintaining equipotentiality and preventing electrical shocks. And thirdly, it facilitates the rapid clearing of faults by providing a low impedance path for fault currents. Always consult the latest edition of the National Electrical Code and consult with qualified electrical engineers or electricians to ensure compliance with all applicable regulations.